let me show you another way to solve for these coefficients, because this way won't always work. So one, I'll show you another way because this way will fail you at some point. So let's look at that problem. It'll also verify that his numbers are right. I believe him. Were there any questions on over here how I broke up partial fractions? Yeah.
On that second one, why is it broken into three?
Anytime you have what's called a repeated root. So we're looking at, the numerator doesn't matter at all. Ignore the numerator, only pay attention to the denominator. Now I'm looking at the denominator. This is a cubic, right? It's a third degree polynomial. You multiplied it out. And I wrote it up here. It's p of x is x squared times x plus 1. So that's my third degree polynomial. This is what's called a repeated root, or a root of multiplicity 2. X times x plus 1, if you were to write it out as all the linear factors. Well, if we were to write it as a over x, right, this one we factored, we had two roots, right? We wrote a over the first root, b over the second root. Well, suppose we wrote this thing down here as a over x plus, okay, there's another root, b over x plus c over x plus 1. Or you might say, well, what if we did a over x squared plus b over x plus 1? Right, those would be two reasonable guesses as to how to break up the partial fractions. And for many years, I tried to create a sequence of problems that would lead students into figuring out how to break up partial fractions. It doesn't lend itself well to discovery. You just get horrible algebra, because if you try this, it just fails. And you can't figure out what your coefficients are. And even when you can't end up integrating what you get. So this will fail you, and this will fail you. And what will work when you have a repeated root is to put it down, a over the first power, b over the second power. And so the reason is because I see a repeated root.
So every time there's going to be a repeated root, it's going to...
Yeah. And so there's these handful of rules until they get really complicated, and then the rules get so complicated you can't even write them down. But I wanted to demonstrate the basic rules. If you have linear factors, just put an a over one and a b over another. If you have a repeated factor, a repeated root, put an a over it and then a b over the second power of it. See, this factor is all by itself, so I just threw in a c over it, right? Now down here we have two things going on. This is a repeated root. X minus 1 appears twice, so I listed it twice. X minus 1 squared. Same rule as I was teaching you here. Now this one isn't factorable. Well, it is factorable. It's x minus 2i, x plus 2i. Okay, I don't want to go into complex numbers. I live in the real world. So, therefore, you can't factor it. Well, you could. You could actually do this as c over x minus 2i and d over x plus 2i and do complex integrals, do a whole bunch of work, and it'll still turn out to be the same answer, but you got to use complex numbers the whole way through. So to avoid doing that, since it doesn't factor, put a linear factor on top, cx plus d over that, and that'll get you there. Those are the three basic rules you need to know. You see a linear factor, put a letter over it. You see a repeated factor, list it twice. You see a factor that won't, a quadratic that will not factor, put a c plus d. If this was an x to the fourth plus 4, which I will not give you, you would have to do an ax cubed plus bx squared plus cx plus d over it. And then your algebra would be truly a nightmare and would require a course called linear algebra to solve. We ain't going there. That help? Who are you? Joseph. We got two Josephs. Where's Stone? Back there? Joseph Stone? No, Simon. Simon. I don't know why he's looking at me. All right. Other questions over there? Okay, so over here, the lesson is, right, the degree of the top was greater than or equal to the degree of the bottom. Therefore, you use algebra to simplify. The algebra says divide the top by the bottom, and what you get are two things, each of which is integrable. This one's easy to integrate, and that one's pretty easy to integrate. So if this is equal to 3 plus 4x plus 10, then the integral of this must be equal to the integral of that. This part's easy, and this part is partial fractions. Okay, so now I want to talk about that 4x plus 10 over x squared minus 2x, which we figured out is the same as, it's going to be a over x minus 3 times x plus 1. Because that's x squared, that's negative 2x, that's minus 3. I don't, you know. Because I'm just trying to do the algebra to find a and b. Okay, when we multiply across, I multiply across by this numerator, since it is x minus 3 times x plus 1, when I multiply here, the x minus 3 cancels. When I multiply it here, the x plus 1 cancels. Okay, now, there's nothing wrong with doing what he did, because I can definitely solve for a by putting negative 1 in here. I'm sorry. I can definitely solve for b by putting negative 1 in here, because that goes away. And I can definitely solve for a by putting 3 in here. When you end up with repeated roots, that method is going to fail you. So I'm going to show you something that's really common sense. I'm going to multiply this out. Ax plus a plus bx minus 3b. 4x plus 10 equals a plus b times x plus a minus 3b. Okay, what's this side? What kind of equation is that? It's a line, right? How many lines 4x plus 10 looks about like this? Let's see if I put a 0 in, I get 10 out. It's got a pretty steep slope, looks like that. How many lines, if I give you another line, I say, look, I want another line that's right on top of that one. What does M have to be? The same thing. There's only one line that's right there, correct? And it has slope 4 and it has y-intercept b. Because if you change b, it's not going to go through the same point down here. It's not going to be the same line, right? I mean, it's not going to go through the same point. So y-intercept. You change b, it does not go through 10. You change 4, it does not have that slope. M and b uniquely determine this line. Okay, well, you have this line equal to this line. They're the same line, then what does a plus b equal? 4. What does a minus 3b equal? 10, because they have to be the same line. If they were a parabola, if there was a 6x squared out front, you'd have an a, a b, and a c or something times an x squared. You'd have a coefficient for x squared on this side and a coefficient, and they have to agree. Now this is a system of 2 equations and 2 unknowns, which you started solving in 8th grade, and then forgot. Solved them again in 9th grade, then forgot. Solved them again in 10th grade, then forgot. Skipped math for a year. Solved them again your senior year, then forgot. Okay, so we're going to remind you. How do you solve it? Well, you could solve for a and plug it into this one, but I'm really lazy. I'm just going to subtract the 2 equations. I'm going to take this equation minus this one. A minus a is 0. B minus a negative 3b is 4b. B minus a negative 3b is 4b. 4 minus 10 is negative 6. So b is negative 6 over 4, which is negative 3 over 2, which is what he got.
How is b minus 3b plus 4b? Can be negative 4b?
It's
Or
b.
negative 2b?
It's b minus a negative 3b. Right? I'm subtracting the equations. A minus a is not 2a. A minus a is 0. B minus, I'm not adding. In high school, they made you multiply through, and then you'd add them, right? But you can and you pass Cal 1, so I can be really mean too. Okay, now I've got B, I can get A, right, just by substituting B back in. So A minus 3 over 2 is 4, so A is 4 plus 3 over 2, which is 5.5, which is 11.5. Sure enough, that's what he got. So Nick did his plugging in correct. I definitely prefer to just grab the numbers I can grab by substituting in, but that will fail you when you have repeated roots. Because when you have repeated roots, there's only one thing, there's going to be multiple variables, A, B, and C, but only -1 makes one of them 0, and 0 makes a couple of them 0, and it won't give you all of them.
Okay, so you found A and B, what do you do then? You plug them back in there?
Yeah, now we're just back to what he did right there. We now know the integral of 4x plus 10 over x squared minus 2x minus 3 is equal to the integral of 3, no, the 3's already gone, is equal to a over x minus 3 plus b over x plus 1. We now know a and b. That's 11.5. Breaking into two pieces. B is -3/2 x plus 1. Those are easy to anti-differentiate because those are just natural logs. That's just 11.5 ln of x minus 3 minus 3/2 ln of x plus 1 plus a constant. The 3 came, okay, I only swerved on the last half.
Okay.
He remember when he long divided, it was 3 plus this. I only started working on the second half. So when he integrated 3, he got 3x. But then he has to integrate both of these, which he had to do via partial fractions, which he did, and he did it right. I just wanted to show you this alternative strategy for partial fractions when you're trying to grab those numbers, because that strategy won't always work, and I hadn't shown you an alternative yet.
Can you show you what you did right there once you plug in A and B?
Once I plugged in A and B, I have two separate integrals. You can pull the 11.5 out front, and then you've just got the integral of 1 over x minus 3 dx. That's just natural log of x minus 3, because the derivative of this is 1 over x minus 3 times the derivative of x minus 3, but the derivative of x minus 3 is 1. So it's just a memorize. That's an easy rational function.
Is there a possible way to not divide it in all? Or is it necessary?
I would say that in the years of teaching integration, I have thrown countless problems on tests that I thought were really easy, and students found me amazingly hard ways to solve them. I am confident there's a way to do this without long dividing, but I bet you'll find that it's worse than this way.
Because I didn't divide it.
Uh-huh.
I got the exact same A and B. My only problem was I could not get the 3x.
Let me see what you did, because I'm sure you did something right. All right, we're over. Y'all stay off the streets, right?